So far we learned about the rate of change of a function in the direction of x-axis and y-axis. What was f of x? F of x was the rate of change of the function in the direction of x-axis. And f of y was the rate of change of the function in the direction of y-axis. Very good. So now I expect you to ask, what if we have a different vector? So remember that the unit vector representing x-axis is just 1, 0, 0. The unit vector representing y-axis was 0, 1, 0. Now I expect you to ask, what if we have a different vector? How do I find the rate of change of the function in the direction of any other vector? That's where we define the directional derivative. Definition. The directional derivative of function f at a point like x sub 0, y sub 0 in the direction of for example, a vector. Now I'm going to introduce a unit vector. Let me use a different color of a unit vector. So the length of the vector is equal to 1. U equals to, the first component is A, the second component is B, is defined this way. This is the official definition, the limit definition of the derivative. The directional derivative of function f at point x sub 0, y sub 0 in the direction of vector u is limit definition, the limit of f of x sub 0 plus ha, comma, y sub 0 plus, for example, let's use hb minus f of x sub 0, y sub 0 divided by h, as h goes to 0. If this limit exists, we have the directional derivative, the rate of change of function f at this point in the direction of a unit vector like u, if exists. Very good. Example. Consider a weather map. This weather map is given this way. Here you have the map of some part of California, and also let's just have a map here, and then suppose we have San Francisco, and then you have Reno, you have Las Vegas, LV, Los Angeles, LA, and well, what do you have? You're going to have the temperature, and you're going to have the temperature at each city. So we know that the temperature is going to be different around each of these cities. So suppose around Reno, it's 50. Around Las Vegas, it's 80. Los Angeles, also around 80. And San Francisco, it's about 60. Okay. We want to know for this weather map, what is the value of the directional derivative? What is directional derivative? In what direction? Of temperature at Reno, what direction? In the southeasterly direction. Okay, very good. So it means that we try to find this direction here, am I right? Very good. So what information do we need here? First of all, suppose the distance between Reno and let me just have some nearby temperature added here because directional derivatives in the direction, it's not globally, it's locally. So we need more temperature around Reno. Suppose here you have, let me see, let's add another temperature around here. Below Reno, it's going to be 60. Let's have the temperature rising, and then around here, we're going to have 70 degrees. Okay. And suppose the distance is going to be, so in this direction, suppose the distance in this direction is about 75 miles. So here, this is the distance. So the rate of change, not in this direction, not in this direction, not in this direction, but in this direction. So Reno, southeasterly direction, in this direction. How the temperature is changing. Is it a negative change? Is it a positive change? Well, by looking at the weather map, you say that, hey, as we go toward the south, the temperature is rising. So we expect to have a positive rate of change because it's increasing. So the rate of change in the southeasterly approximately is equal to, well, the rate of change of the temperature difference in the temperatures divided by the distance. So it's going to be 60 minus 50 with the given distance 75 miles. So this rate of change is approximately 0.13, for example, Fahrenheit per mile. This is the rate of change. We expect this rate of change to be positive because the temperature is rising in this direction. So if I, for example, change the direction, for example, if I go up, the temperature might be decreasing. So if I change the direction, I'm going to get a negative rate of change. But since it's southeasterly, 50, 60, and with the supposedly given distance, 75 miles, I can find the rate of change of the temperature, which is 0.13 Fahrenheit per mile. That's the application of directional derivative, but eventually we're not going to use the limit definition. We're going to switch and use the partial derivatives to help us to calculate the directional derivative. In the shortcut here, let us write down the shortcut. If your function is differentiable, if we know about that, if you're sure about that, we can prove that. Note that if f is differentiable, then the directional derivative of function f at point x sub 0, y sub 0 in the direction of unit vector u follows the partial derivative of f with respect to x at x sub 0, y sub 0 times a, the first component, plus the partial derivative of f with respect to y at x sub 0, y sub 0 times the second component. It happens that f of x and f of y, they represent a vector function that we call the gradient of function f. So nabla f, the gradient of function f at any point, is a vector function. Partial derivative of f with respect to x and partial derivative of f with respect to y is called the gradient of function f, which is a vector function. By using this definition, the directional derivative of f in the direction of u is just the dot product between the gradient of f, dot product gradient of f, and the unit vector u. So this is the dot product. Let's go over one example. I'm going to write these formulas up here. So if f is differentiable, the directional derivative of f at any point in the direction of unit vector u, guys, u needs to be a unit vector, is equal to f of x, and u is a and b, a comma b, f of x, a plus f of y, b, or the gradient of f, that vector u, where the gradient of f is the vector function f of x, f of y. Example. Suppose I give you this function. Let f of x and y be equal to x squared, y cubed minus 4y. Find the directional derivative of f at point, what is the point? 2 and negative 1 in the direction of vector v, which is defined as 2 and 5. Okay, guys, remember that in our definition, U needs to be a unit vector. Unit vector. What's the meaning of that? It means that the magnitude of U, the size of U, which is a squared plus b squared, it must be 1. If it's not, you have to rescale your vector. First, check if the vector is a unit vector or not. Okay, the magnitude of vector v is square root of 4 plus 25, which is equal to square root of 29. This is not 1. So v is not a unit vector. So what's the remedy for that? What should I do here? Rescale that. Vector u is vector v divided by the magnitude of vector v. That way you create a unit vector. So your vector is, where is my first component 2 divided by square root of 29, comma 5 divided by square root of 29. Now we have a unit vector. Okay. Now follow the formula. Okay, so the formula says the directional derivative of f at point 2 and -1 in the direction of unit vector u is, well, what do I need? I need the partial derivative of f with respect to x, which is 2xy cubed times the first component, 2 divided by square root of 29, plus the directional derivative of f at point x sub 0, y sub 0 in the direction of unit vector u has the second element, f of y, partial derivative of f with respect to y, which is 3x squared y squared minus 4 times the second component, 5 divided by square root of 29. Now let us plug in and see what do we have. My x is 2, my y is -1, so this guy becomes 2 times 2 times -1 to the third, 2 over square root of 29 plus 3 times 2 squared times -1 to the second minus 4, 5 over square root of 29. Well, after simplifying the whole thing, you're going to have, let's see, you have -4, and here you have, okay, you get 32 over square root of 29. So the rate of change of the function at this point in the direction of this unit vector is going to be a positive number. So we have a positive rate of change in that direction. Positive rate of change.